Get my audio 100%. Thank you very much, Tony. Appreciate it. Okay, so looking at an equation like this, so let's say, again, V, the voltage, bless you, ZT is some function, I'll call that function G, I don't know why in my notes I haven't, but G, F, doesn't matter. Some function of Z minus T over square root of LC. Okay, so what I just said is you have, this represents, depending on what the function is, this represents the function traveling in the positive Z direction with as time ticks. So if this is my transmission line and it obeys this equation, and this is my positive Z direction, this would mean that if I had some kind of a waveform, I'm drawing you guys like another waveform, it, as you know, I go up, so if I go in, so this is at t equal to 0, at t is equal to delta t, I would get this would get shifted over by some distance. So it's traveling in that direction, in the positive Z direction. Okay, as a function of time. And the distance, so assume this is, let's call this Z equal to 0. So this would be like negative Z, this would be positive Z. The distance that the new peak would be at, so at t is equal to delta t, would be Z is equal to delta t over, Z is equal to delta t over square root of LC. And again, the only thing I've assumed is the inside has this form. So all I had is plug in zero here. Okay. If I plugged in 0 for time here, I would get G of Z. If I put in delta t here for time, okay, I would get Z minus delta t over square root of LC, which means that G of Z would have moved over by that amount. Okay? You guys with me? So this is a few added implications. It tells you, so Z has units of distance, right? And T obviously has units of time. Okay, so square root of LC is going to have units of time over distance. It's just inductance and capacitance. I think if you just do farads and capacitance, that's what it ends up looking like. So this delta T over square root of LC is going to have units of distance. You guys with me? I'm just sort of doing the math thing. I'm not coming up with some new definition of inductance and capacitance, but that's what square root of LC looks like. Okay. Okay. So now let's say, what else do I want to say about this? That's good. So the other thing I said was that a solution to this wave equation, oops, did I say this? Yes, I did say it. So a solution to the wave equation could be either T minus square root of LCZ, or it could be T plus square root of LC. Okay? So what does T plus square root of LC over Z look like? And that looks like, so if V of ZT is equal to G Z plus T over LC, what that would look like is if my waveform didn't work. Sorry guys, I'm being too clever here. Let me just this the same waveform. So it looks like it's traveling in the negative z direction because I'm doing z plus t over LC as opposed to z minus t over LC. And both of those are permissible answers to our wave equation. Okay, so if I go, this would be, whoops. This would still be z equal to 0 at t equal to 0. This would be z is equal to negative delta t over square root of LC. Okay, so if I just, my time is still going in the positive direction, but the wave's going in the negative z direction, it's just a positive z direction. Okay, so this means both of those are possibilities in a transmission line. In a transmission line, my waveforms can go either sort of in this positive direction, away from the source that launched them, okay? Or they could be coming back towards the source. Both of those are possibilities, okay? In a general case, waveforms that are going in the positive z direction in our world are been launched by the source. Waveforms that are coming back are stuff that got reflected for some reason. They hit something along the path that didn't fully absorb them, and they just got reflected back. So it could be this waveform, it could be another waveform, whatever got reflected back. And you have to worry about both of those in a transmission line design, because if you guys remember, I did that square wave last time. I don't know if you guys remember, but like I was saying, if you had an improperly designed transmission line and you were looking at your scope, instead of seeing a square wave, you would kind of see this. You guys remember we talked about that? It's because stuff getting reflected back and forth here, and it kind of dies off. These reflections are waves that went to the source, came back, so you get stuff going in both directions. Okay? So generally, this is very generally, you do not want this. And for sure in a digital system, you do not want this, because this is just screwing things up. Right? I want this, generally. If I got reflections, I'm going to get this, and generally it's not good. But it's not always the case, but it's possible and it does happen. And that's because both of these forward-going and negative-going wave, forward-going and backward-going wave are possible in a transmission line. So it's not just a mathematical thing, it does really happen. Okay. And so, okay, so from this, we can also say, what's the velocity of this wave? So I'm launching these bits, these functions, these waves in there, there's a velocity, okay? Like how fast are they going down? Well, so they travel delta z in delta t time. And the delta z was square root of t, delta t over square root of LC. So this is, not to be mistaken with voltage. So let me just say velocity. So that's equal to delta t over square root of LC over delta t, which is equal to 1 over square root of LC. That's a good thing to probably, go ahead.
Is this only in the positive direction sense?
It'll be the same in the negative direction. So basically the only difference in the velocities will be the sign, so which direction they're going to, but the value is that much, okay? So this velocity also tells you like, hey, if I have a 10-foot long transmission line, how long is it going to take for that bit to get from one side to the other? So it's a really important thing, this velocity of how fast you go through the transmission line. Okay, and you can basically you can kind of design that, how fast you're going through the transmission line, or how much delay you get through a transmission line given a certain distance. When I say stuff like that, I mean within reason. just the materials we have, the physical sizes we have, is not gonna let you do any old thing you want here simply, right? But you can tune the delay through a transmission, because you can tune the velocity. And it's just a function of the inductance and capacitance per unit length. So that's an important thing. Okay, so let's look at some specific solutions for this G or F function. So let's look at specific solutions, some specific solutions. And so what's pretty common, it's like you guys have seen, like we're launching sine waves, sort of stuff like that into these transmission lines. So generally, possible solutions are things like cosine, sine. The complex exponential is sort of like a combination of those type of functions. Okay? A square wave is a combination of cosines or sines at different frequencies if you do a Fourier transform breakdown of it. So these are pretty sort of possible solutions. So specifically what it'll look like is cosine of omega t plus minus beta z as a general case. So remember the form of the solution was t plus minus z. Okay, instead of LC, I just put this beta to make it more general. Okay, and I put this omega, which is as we'll see what that means, right? It's a function of how it's changing with time, the waveform, as a general function. Okay. You guys with me? So this is a sinusoidal wave. So these look like sinusoidal waves. Why sinusoidal? Well, again, cosine, sine of sinusoidal. And this is a combination of the two. And they're waves because they have this form of t plus minus something z. So it's a wave. Okay, so we're going to look at these kind of things. So omega is something called angular frequency, and it's equal to 2 pi times the frequency of your sine wave or cosine wave. So this is in hertz. And omega has got units of radians per second. And beta is called the propagation constant. How am I doing with my speed, guys? Going fast, slow, too slow? I'm just worried I'm going too slow for you guys. No? Because I'm like, I remember. Huh?
The pace is good, but the writing's hard to read.
I'm sorry. I know this to be true. I know this to be true.
It might be the lighting too. I don't know.
Nah, it sucks. Maybe if I'd hate to do this, but I'll sit down like a scribe and see if that helps my handwriting any. Okay, so I really, really do apologize for that. It's a big problem. Especially when I get excited, as I am now, extremely excited. Angular frequency. But please let me know. Just stop me and say, we can't read your stuff. Yes, please.
Could you just do
Write a little bit bigger?
Yeah,
Okay.
I can read what you're writing, it's just kind of small.
Gotcha. Let me do this. And I'll just, maybe bold will help me.
There's no way to take the whole room projected.
The what, sorry?
Like, you know how it's a shirt almost like projected?
Oh, yeah. You know, maybe it's a function of how you guys are gonna make me do this. Let me see if I just flip this over, would it work? Is better? Now is it too big? The thing is I hate writing like this, and I just sort of like, don't even ask me. Okay, so now is it too big now, or is this a good size for you guys?
Yeah.
This is good. Okay, good. Okay, so this is called angular frequency is equal to 2 pi times f, where f is in hertz, and omega has got units of radians per second. And beta, so this is the definitions, is called propagation constant. Okay, so I'm talking in terms of general terms here. So beta was, if you guys remember, in the specific case of our LC sort of transmission line was, what was it, 1/square root of LC, right? And you guys saw what it did, right? It's sort of saying how fast is this thing moving through, right? You guys with me? So what is this angular frequency? Okay, we didn't have that in our general. There was nothing sitting next to the t and my f function before, right? Now I'm saying, hey, it's like a cosine wave. It's changing with time. So something's changing with time in my waveform that I'm launching. And generally, it's gonna, that in the case of a cosine or a sine wave, it's just gonna have a frequency. That's the only thing. A cosine is a pure wave, right? So all I have to do is to say the frequency of the cosine, and you guys know how it's gonna change with time. You guys with me? This is the kind of stuff that confuses the hell out of me. Now it's making a little bit more sense because I'm saying it. You guys with me? If you're not, let me know. So this f is the frequency, like it'd be 100 megahertz sine wave I'm launching in this, or 200 megahertz, whatever. And it's just putting it into sort of angular or radians, okay? By multiplying it by 2 pi f. So I'm giving it in radians per second. Why? It's because like a cosine wave, it kind of repeats itself. So people kind of like to talk about it in those terms. Like how long does it take to get from a peak to its row in terms of zeros and pi's and 2 pi's as opposed to hertz. It's kind of a more general result. You guys good with that? I have a feeling I'm telling you guys stuff you already know. Okay, so these are definitions, okay? And general form of the function. And then we have this thing, if you do the ratio of your angular frequency to your propagation constant, it is equal to, in the case of our transmission line, it's 1/square root of LC, which was our velocity, okay? But it's kind of called the phase velocity in transmission lines, and it's got, looks like U of P. So this is kind of like good to remember. And then we have this thing called dW over the the rate of change of our angular frequency with propagation constant is called U of G, or the group velocity. Yeah.
Going back to the angular frequency, it's too high because of how long it takes to complete like the cycle.
Yeah. So if you go 2 pi in a cosine wave, if you go through 2 pi phase, you can't tell that anything changed at all, right? You go back to the same thing you were. So that way you don't have to worry about, sort of gives you a general equation. It doesn't matter if that sine wave, cosine wave is running at 100 megahertz, gigahertz, 1 hertz. It's just easier if you keep track of in terms of how many radians per second it is as opposed to how many hertz. Yeah, but that's exactly right. So you're going from, again, the only reason we're doing this, we can do this, is because we're talking about cosine, sine functions that repeat themselves. If that wasn't the case, then it would be, you couldn't do that. Okay? This is what always confused me. This is why radians, why hertz, why radians per second, why hertz, whatever. I think that's the bottom line, is it helps you deal with cosines and sines in a more general form. Okay, so this group velocity, so that's your phase velocity. What's a group velocity? So I'm not a surfer, but again, I'm trying to come up with analogies of I suffer in the surf, let's put it this way. I'm not a surfer, but I suffer in the surf. So the group velocity, so you guys have probably heard maybe surfers talking about, oh, there's a group coming, right? Which is a bunch of waves, okay, coming. And so to me, group velocity means sort of as a whole, how are these guys moving? Okay? So let's say instead of a cosine wave, it almost doesn't make sense if you had a pure cosine. But again, a square wave is a bunch of cosine waves all added together. If you do a Fourier transform, you'll see it's a bunch of cosine waves at different frequencies and stuff, but they're all sort of hanging together to keep that square wave going when they add together. The group velocity is sort of telling you that how fast all those different cosine waves are moving together as like a set. Is how I look at it. It may be the wrong analogy, but that's a group velocity, okay? And then if your group velocity, so if U of G of W, if this is a function of frequency, okay, then you have something called, then you get dispersion. Okay, so this is kind of a little bit of an advanced concept, and we're not dealing with dispersion quite yet, but dispersion is something you'll see at high speeds in transmission lines. Dispersion means a cosine wave at like 100 megahertz is going to travel through at a different speed than a cosine wave at 200 megahertz. That's what, if this group velocity ends up being a function of radians per second or a function of frequency, you get this dispersion, which means you moving at different things at different frequencies move at different speeds. Okay, which is a bad thing. Dispersion sucks. Okay, because you always get it. But it means that even if I didn't have any loss in my transmission line, if I put a square wave into one end, because of this dispersion, it's going to start getting distorted. Because if it wasn't getting distorted, so remember the square wave has a bunch of different sine, cosine wave components that are getting added together at specific frequencies. If I'm getting dispersion, the high-speed components are moving at a different speed generally than my lower speed components. Everybody's moving at a different speed, so it means that if I did an FF or a Fourier transform of my square wave further down the line, it's going to look like a different Fourier transform. So my waveform's getting distorted even when there's no loss. And you see that all the time, by the way, in high-speed digital communication is you're putting in a waveform in, there is dispersion, you've got it terminated nicely, you've got a characteristic impedance, except things are, you get a beautiful square wave in one side, and you get something that looks kind of like a square wave on the other side. So there's all these things, there's loss, there's improper termination, there is, and dispersion, that they're all sort of working against you to get a clean waveform through your transmission line. Okay, so I'm just mentioning this to be complete. Okay. I'm convinced, well, anyway, half of engineering is to confuse the students. So here we go. Put your seatbelts on. Okay, so I'm going to rewrite this equation. I'm going to write this equation again, z of t. So let's say I'm going to, again, sine wave, cosine wave, right? Let's say it has an amplitude. Okay, which is, so this is a positive z going direction. Okay, so that's a possible solution, right? And another possible solution is v0 minus cos of omega t plus beta z. So this is minus z going direction. Can't help myself, I gotta distort my handwriting. So, what I'm saying is, the notation we're gonna use is if a waveform is going in the positive z direction, we're gonna call that, the amplitude of it is plus, to imply it's going in the positive direction. If it's going, so it's gonna have this minus sign. If it's going in the negative direction, we're gonna call that V0 minus. These are voltages, like it's basically the amplitude of voltage. Okay? This is not the difficulty. Here comes the difficulty. God, I'm embarrassed to do this to you guys. But it has to be done. I'm not responsible. Okay? So, because the equations, only, because the equations are going to get complicated, okay, with cosines and sines and blah, 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 people have come up with a shorthand notation, okay, called the phasor notation. It has nothing to do with Star Trek. It's not some new physical phenomenon. It's just a shorthand notation with how cosine and sine waves are written down. Okay, it's called a phasor notation. And then so what we're gonna do is we're gonna look at this phasor notation, and then we're gonna go from this is sort of the normal world. We're gonna go into this phasor notation, and then when you want to go back and figure out what our voltages and currents look like, we're gonna go out of the phasor equation back into the normal world. It's just mathematical shorthand. So don't try to understand it. So in the phasor notation, this whole thing, okay, is just called V plus Z of t. Okay, so I just took the cosine and said, you know what, if I tell you this is a phasor, remember it's gonna look like this, because I don't feel like writing this cosine of omega t minus b, whatever, for the rest of the lecture. Phasor notation is just a notation. At the end, we're going to go back and add this stuff. You guys with me? Confusing as hell? Yeah? I don't know why they did this. I was perfectly happy to keep writing cosine of omega t. And then I'm going to call this, so I wrote this badly. Let me put it this way. It's going to actually look like this. V plus with a squiggly head, z of t. V minus with a squiggly head, z of t. So whenever you see that squiggly head, it's this phasor notation. So phasor notation means that I'm not putting in the cosine sign. And that's all that means, okay? Okay. Okay. Guys with me? Guys okay? All right. So for the time being, so for now, we'll assume omega is constant. Okay? No, sorry guys, I jumped the gun here. Sorry, I screwed something up here. So let's just call this is still not the phasor notation. Let me just write the phasor notation here. So erase that, erase that, erase that. So phasor notation is going to be, so V0 plus cosine of omega t minus beta z with the phasor notation is going to look like V0 plus e to the minus j beta z. Do I want to tell you guys this? Okay, let me tell you the background on why this is actually.
Professor?
Yeah,
So this is the theta notation, not the one you wrote earlier?
yeah, this is the phasor notation. So let me take a step back. Sorry guys, I was trying to avoid this full explanation. This is correct, but I'm just going to erase it for the time being and step through how we got to here. Okay?
Oh, so the one you did write was also?
No, that one was bogus. This is correct, but I'm gonna put this aside for a second. I'm gonna tell you how we got here. Okay? I was trying to avoid that, but obviously got me in trouble. Okay, so V at z of t, if you just look at the positive side, okay, is if you write it in sort of exponential form, right? It's gonna look like V0 plus e to the j omega, whoops. Oops. So, guys, if you remember, e to the j omega t is cosine of this guy plus j times the sine of this guy. Okay? So if I'm just looking at, so this would just equal to cosine of omega t minus beta z. Guys with me? No? So let me just write it all out. So so this guy is cosine of omega t minus beta z plus j omega t minus, whoops, Do you guys remember this? This is what it looks like. If you take e to the j of omega t, it's going to be cos of omega t plus j sine of omega t. Okay? So if I do the real value of this whole thing, that ends up just being v0 plus cosine of omega t minus beta z. Sorry about my handwriting, it's degenerating again, which is this guy. Yeah? I'm just rewriting the same thing in different ways, yeah.
What is the RE?
Oh, the real part of.
Oh, okay.
Okay? So this is kind of like a crazy way to write. If I was going to write this thing in this crazy way, Sorry, I'm just giving you guys, this is why I avoided the step, but it hosed me up. So, what this phasor notation is saying is, I'm just gonna remember this, and I'm gonna get rid of that, because I'm gonna assume that omega is constant. Okay, so I'm just gonna worry about V0 plus e to the minus j beta z. That's what the phasor notation is saying. Don't blame me, guys. That's what they do. Okay, it just seems like a lot of steps, but I can't help it. So if you guys with me though, how we got to this step? You guys with me how we got to this guy? Okay, and then backwards how we got to this guy? And that this guy is the same as this guy. So the real part of V0 plus e to the j omega t minus beta z is the same as V0 plus cos of omega t minus beta z, which is what was our sine wave going through, yeah.
Real meaning we're ignoring that imaginary j.
Yeah, because, so again, for now, we're assuming omega is constant. So I'm going to say, hey, omega is constant, so I'm not going to keep writing omega. I'm just going to forget about it. So I'm just going to write, so I'm going to take this omega, this part out of it. Yeah. So I'll stop writing the e to the j omega t part. Okay? And so in the phasor notation, I'm just going to say it's going to be V0 plus e to the minus j beta z. Okay? So in my math, I'm just going to write this. At the end of everything, when I'm done, I'm going to go back and add the e to the j omega t. So I did all that stuff just so I wouldn't have to keep writing e to the j omega t, something that's not going to change in my equations. You guys with me? That's called the phasor notation. All right, sorry guys. Okay. The things I'm compelled to do. So let's think about why I want to do this phasor equation, phasor method of doing it. So here's an example. I was hoping we wouldn't have to go through this, but so let's say I want to take the derivative with time of a waveform. So let's example of why this phasor notation. Okay, so let's say I want, whoops, sorry guys. I want d by dt of a waveform. Is my handwriting still somewhat readable? Thank you guys. So let's say I want to do d by dt of v0 plus cos omega t minus beta z. Okay, which is equal to minus omega. I'm just taking the derivative with respect to time of that waveform. No phasor notation, nothing at the moment, okay? Omega t minus beta z. So I'm just taking the derivative of cosine. And this is, again, with this thing I'm using, this is like writing the sine thing is just a real part of j omega v0 plus e to the minus j beta z e to the j omega t. You guys with me? Jump in with any questions, because I'm semi-confused myself. Just kidding. Okay, so in the phasor notation, so to get this in the phasor notation, to get into phasor notation, I'm going to do the following. I'm going to drop mention of real to, I'm going to drop e to the minus j omega t. Okay, so I'm going to say the answer to this thing in phasor notation is j omega w0 e to the minus j beta z. And I'm going to do all my math like that. And then once I'm done with my math, I'm going to go put in the j omega t back in. And I'm going to put the real part back in also. Remember that I'm doing that. Okay? And I'm going to call this the phasor. So this is the phasor, which is the squiggly head thing, v0 plus of z. So just play along for now, and as we play with it, maybe it'll make more sense. God, I apologize, guys. I apologize. Okay, so basically, with all that, basically again is d by dt v0 plus cos of omega t minus beta z. Okay, so if I just look at this in the phasor notation, okay, it looks like I've got dt v0, the phasor is j omega v0 plus the phasor vz. Okay, so in the phasor domain, d by dt looks like I'm just multiplying by j omega, and integral by dt looks like I'm just dividing by j omega. Just like another transform. I don't know how to put it. Sorry, guys. Any questions, guys? So bear with it for now. Hopefully it'll, we'll just work with it and see how confused you get down the line. We're just going to do all our math with these phasors. And at the end, we're going to remember that we have to put in back the e to the j omega t in the real part. Okay. Yeah.
And so the process is we're just changing it to a phasor notation, and then we're going to do the math in there and then change it back.
Yeah. So it's sort of a convenience thing, but it's very confusing to begin with. Hopefully it'll get less confusing. Do you guys feel like taking a little bit of a break? Or keep going? What's the vote? Break. No? No? Come on, guys, somebody. Spit something out. Break. All right, take a little break. What's that? Oh, okay. Well, okay, let's take a little bit of a break. Let's 10-minute break and get back to it. Yeah.
You're gonna upload this, right?
Yes. If somebody reminds me to, please do.
Yeah.
still recording? It's still recording. Okay. I'm gonna stop it recording.